Hello everyone, and welcome to More Realistic Assessment of Slabs in Buildings, which is a webinar that will provide you with an overview of our yield line analysis software, LimitState SLAB, and explain how you can use it to analyse a range of reinforced concrete slab problems, often demonstrating that existing slabs have reserves of strength that other methods might miss. Just to introduce myself, I'm Tom Pritchard, the LimitState Product Manager, and I'll be presenting a section of today's session, and I'll also be joined by Matthew Gilbert, who is the Managing Director here at LimitState. Today's webinar is due to last around 45 minutes, and we should have a few minutes at the end for questions, which you can post at any time using the question box in the webinar interface that you should hopefully have in front of you. We always try to answer as many of your questions as we can, but this isn't always possible in the time available, so we do apologise if we don't get round to yours. However, we will follow up on all queries in the days after the webinar, so everyone should get a reply. Also, if you think of anything after the webinar has ended, you can always contact us via email on info@limitstate.com and we'll get back to you. So, for the first part of today's webinar, I'd like to introduce you to Matthew Gilbert, who will be speaking about the background of automating the yield line method.
Thanks very much, Tom, and thanks very much to all of you for joining us for today's webinar. Okay, so the first slide that I was going to show just shows a few examples. Examples on the left are examples that you might see in textbooks. Yield line patterns for simple slab configurations. The slabs on the right, more complex. So we've got a slab with a hole, and we've got one of the building floor plate slabs that we'll consider later on in the webinar. So the key thing is to move from these sort of textbook type examples on the left to be able to solve the more complex practical slab configurations that you see on the right, and that's what LimitState SLAB is designed to do. Okay, so in terms of contents, number of things, some of them quite brief. I'll say first of all a few words about LimitState the company, then move on to talk about the yield line method and give you a quick demonstration before explaining how it works, and also some benchmark examples. Tom will then come back and look at more in-depth applications of the software before wrapping up with conclusions and questions. Okay, so a few words about LimitState. We're here to provide engineers with powerful, practical analysis and design software, primarily focusing on ultimate LimitState criteria. We're basically using methods that have hitherto been sort of confined to universities and making those available. So we're using optimization technology to do that. And because we're a company, obviously we focus on making sure the software is robust, well validated, as well as easy to use. And we've currently got customers in more than 30 countries worldwide, including both big companies and much smaller companies as well. In terms of the software that we develop, we kind of sit between purveyors of hand calculation or automated hand calculation software at one extreme, and developers of what we might call advanced tools, for example, based on nonlinear finite element analysis or discrete elements at the other. So what we're trying to do is deliver the best of both. So we use numerical rigid plastic analysis methods to allow us to provide pretty much instantaneous results to potentially complex, geometrically complex, perhaps also with complex arrangements of material properties, provide solutions very, very rapidly. So moving the kind of techniques that have been confined to hand analysis and bringing them into the realms of practical analysis and design. In the case of the what we're looking at today, concrete slab analysis, one of those tools that's been confined as a hand analysis tool has been the yield line method. So it's long been understood that the yield line method can identify hidden reserves of strength. However, whilst it's been confined as a hand analysis tool, its usage has been somewhat limited. So what we're able to do is to actually extend the applicability of that and ensure that you, the engineer, is not concerned that you're missing critical yield line patterns, because clearly that's potentially a concern if you're applying this to real life buildings, whether it be for assessment or for design. So just a few words about the yield line method for those of you who are not familiar with it. The whole sort of idea of yield lines probably goes back to a paper that appeared in the Structural Engineer Journal almost 100 years ago. It was identified that when rectangular slabs were tested, they appeared to get hinge lines or yield lines defining the mode of response at collapse. So this concept was picked up and developed much more fully by Johansson some years later, and it was later shown that the yield line method is actually an upper bound plastic analysis method. So in terms of what's good and less good about the yield line method, good things are that you get an estimate of the collapse load directly, and the key thing is that you can end up with very economical designs or more realistic assessments of the capacity of existing slabs. The downsides of it are it's non-conservative or unsafe if you choose the incorrect mechanism, and that's been a big problem with usage as a hand analysis tool. Much less of an issue if you're using a computer-based technique such as LimitState SLAB. Another con is that it only considers flexural failure, so if there are other failure modes, punching shear, you will need to check those. And obviously, as it's an ultimate limit state method, it doesn't give you an indication about deflection, so you need to check those using other means. In terms of interest in the method, in sort of 1990s and beyond, Cam Middleton and colleagues at the University of Cambridge looked at quite large numbers of concrete slab bridges, and they identified that if you used the yield line method or plastic methods in general, you could realize significant benefits in terms of load carrying capacity. So on this slide, the green bars show the plastic capacity, the red bars show elastic capacity. So you can see a large number of those bridges were identified as having the capability to carry 40-ton vehicles when conventional elastic methods had indicated that they were substandard. The way that he did that was to basically crank through a series of potential failure mechanisms. We've actually got a library of 27 shown on the right of the screen. So very, very a nice piece of work. The only downside, however, is if you've got a particular bridge geometry where the critical failure mechanism isn't represented by these 27, then you will end up with an unsafe estimate of capacity. And when we come to buildings, we're generally dealing with more unpredictable or complex geometries, and this kind of approach is a little bit less amenable. However, certainly yield line methods have been considered in the context of buildings many times. What was done at the Concrete Centre 10-15 years ago was interesting. They basically used yield line design methods to design floors in the Cardington European concrete building project, and what they found was that the use of yield line methods led to reduced tonnage of reinforcement and also simple patterns of reinforcement. So compared with elastic design, where you might have lots and lots of bar marks per floor, you end up with much more modest numbers, but also low tonnage. In terms of applications to assessment, so you've got an existing building where you need to design potential strengthening for reuse, or you just want to check that an existing building is fit for a different purpose, then the yield line method really comes in extremely handy. You can avoid expensive strengthening works, and I mentioned earlier that one of the problems with the yield line method, it doesn't give you any indication of deflections. If you've already got a building in place, then potentially you can install water tanks, fill those up, measure the deflections, and go get around that problem that way. Actually experimentally verify that deflections are satisfactory. Okay, so just before we move on, I'm just going to start up the software and just show you how quick and easy it is to use. As I mentioned earlier, Tom Pritchard, my colleague, will have a more in-depth demonstration a little bit later. But when you start the software, you can you're given a chance to start a new project. What I'm going to do is just start an empty project. I'm going to actually put a canvas down so I can quickly sketch out a slab using the very simple CAD functionality in the software. So I'm just going to sketch some configuration that my building slab may look like, and this is quite an unusual one, but obviously you can put in whatever geometry you want. If you have a CAD plans, which very often you will, you can read the geometry in from those, and Tom will talk about that a little bit later. So I've got a simple geometry. What I need to do is assign supports, loads, and materials, basically. I'm not going to spend time worrying about materials. I'm just going to apply a built-in property, unit plastic moment of resistance. So that's a sort of isotropic slab property. I'm going to actually assign the same boundary conditions to all the external boundaries. I'm going to say that they're simple, for example. And lastly, I'm going to assign a pressure load to the whole slab. So after 3 or 4 clicks, I've got a problem set up, which hopefully, if I click the solve button, I will be able to get a solution for. And you can see very, very quickly, almost instantly, we get the predicted failure mechanism, and in the output box we actually have a solution, and the solution is actually an adequacy factor. It's the multiplier on that unit load at collapse. If I put in real values for all the loads and moment capacity, and also I'd put in partial factors according to design codes, then the adequacy factor would actually be an over-design factor, or sort of safety factor. But you can see very, very, very easily we're able to get the predicted yield line pattern. And it's a yield line pattern that actually would take you some time probably to analyze by hand. And clearly I can change things around. Are these supports that I've had highlighted really there? If they're not, how much difference does it make? So if I solve again, the adequacy factor was 3.7, it's gone down to 2.5. Okay, maybe those supports weren't there, but actually I've got some continuity over these other supports, so perhaps having a fixed representation of those would be more realistic. So I can select those and change those very, very easily. Oops, I've just clicked off it. So change those to fixed and see how that changes the mechanism. And actually it changes to a very simple mechanism, and we have a nice simple solution of 4, which is above the previous values that we had. And then lastly, before I move on, let's say actually on reflection, these external boundaries are not actually free, they're actually simple, and see how that changes the situation. And you can see we change from a really simple mechanism to a much, much more complex mechanism. And so this is using rigorous methods to identify what the critical mechanism is, whatever the geometry may be. Okay, so hopefully that gives you an indication of how quick and easy it is to use. The question is, how does it work? Where's the method come from? Well, enabling technology is something called discontinuity layout optimization, or DLO for short. It's a bit of a mouthful. Publication of this method in 2014 for Slabs, some publications on application to other problems some years previous to that. In terms of how the method works, if you have a design domain, load supports, what you do is discretize that design domain, slab domain with nodes. You connect each of those nodes to every other node with a potential yield line, and then use optimization, linear optimization in this case, to find a minimum energy solution, as in the red and blue yield line pattern that you can see on screen now. And when we've applied this to benchmark problems, we've got very, very accurate results. So there's actually 3 different square slab problems here, benchmark problems. First one, simple supports with a UDL. We end up with the correct solution, which is a simple sort of X-shaped geometry. When we change those supports to be fixed, we get a very close representation of the more complex mechanism, which is known to be critical for that case. And if we put a point load instead of a distributed load, then we get a circular fan mechanism, which again is the known critical mechanism. So we get very, very good results for those academic benchmark problems. And because it's general, we can assign much more complex geometries, and we can still solve those without problem. And for all the problems that we've tried, we've had better solutions using DLO than any other method in the literature. And then the last example I'm going to consider is one that was actually considered in the Concrete Centre guide on yield line design some years ago, I think 2004. This is an apartment block with quite a complex geometry for the floor plate in London. And what they did is design that floor plate using yield line methods. In that case, what it meant was they had to consider a series of patterns, yield line patterns. So if you can see on the diagram on the right, you can see pattern 1, 2, 3, and so forth, pattern 8, 9, 10, and also a folding plate mechanism on the left. So what they had to do was do the calculations for all these different patterns until they found the most critical one. And must have been a fairly time-consuming job, made more difficult by the fact that we don't have, orthogonal sort of beam column grids. We have got these isolated columns which are positioned irregularly. In terms of the software, we entered the details of the geometry of this slab. Many thanks to the original designers for providing that, and within a couple of seconds we end up with the solution. And that's actually relatively similar to the folding plate solution, which was one of the options I showed on the previous slide. It's a bit more complex. The extent of the mechanism is a little bit greater in this case than the one that they suggested, and as a result, the result that we got was something like, if memory serves me correctly, about 7% more critical. So in other words, they overestimated the capacity of the slab by about 7%. Although to compensate, they had a 15% margin of safety. So actually, their work was perfectly safe. If you're interested in this example, there's actually more details in a paper that was published last year. It's an open access paper, so anybody can get hold of it, published in the ASC Journal of Structural Engineering. Okay, so I'm going to hand over now to Tom, who's going to pick up on some slightly more detailed example problems.
Thanks, Matthew. So I'm just going to go through a couple of example problems. One of them is to deal with some prop loading on a building that is being repurposed, and the second one is to do with some plant loading where people want to drive, in this case, a mini digger across a slab and see what the result might be. So for the first case, we're looking at prop loading in an existing multi-storey office building which is undergoing some repurposing work, so of the type that you can see here on the right hand side. The first floor slab is to take some props while work is being carried out on the floor above, and opening up works have provided some details of the current slab and beam reinforcement so we can use them within the software. And the question that we want to ask ourselves is, can the slab carry the proposed loading from the props at the ultimate limit state? So if I just open the software again, and we have Matthew's file there, or close that, what I'm going to do, and as Matthew mentioned, there are several different ways that you can get your geometry into the software. You can draw it in yourself like Matthew demonstrated earlier. You can use one of the built-in wizards to set up a very simple rectangular slab or skewed slab with a hole in it maybe, or you can use a CAD generated DXF file to bring in more complicated geometries, and that's what we're going to do in this case. So if I go to File and import the geometry, we can see here that I've got a DXF that I've already set up, and if I click Open, then the DXF import dialog just asks me a few questions about the extents of the problem and whether I want to import one or more or all of the layers that are there in that particular DXF file. In this case, I'm going to import everything, so I click OK, and you can see here that we have a set of different solids that have been imported. And essentially what the DXF import does is look for closed loops of lines within the DXF file and then treats each of those as if it were a solid zone in its own right when it brings it into the software. So that's what we've done here. So we have a geometry that we've brought in. The first thing we want to do now is look at applying some material properties for our slabs and beams to this geometry. So you can see here on the left hand side we have a structural definitions explorer with a few of the built-in material properties. What we want to do is actually make a new structural definition. So if I right click in there, you can see here that we get a dialog that then allows us to type in all the different material properties that we want to use. So for this one, what I'm going to do is have a slab, and I'll give it a lightish bluish grey colour, and then we have all the properties that we need to put in are actually the plastic moment resistance in hogging and sagging, an angle for the reinforcement, and then thickness and a unit weight should we wish to consider self-weight loading from the particular zones that we apply this material to. So in this particular case, what we're going to do is look at having a value of 151 in both hogging and sagging. Obviously, if the top reinforcement was lower in terms of capacity than the bottom reinforcement, then we could put that in but in this case we're going to keep it the same in both cases. We're also going to keep our angles at 90 degrees to each other, so basically a Cartesian grid of reinforcement, but you can, if you want to put skew reinforcement in there, adjust these angles accordingly. For the thickness, I'm just going to say that a slab is 0.7 meters thick and the unit weight is 24 kilonewtons per meter cubed. So we've defined a slab, and you can see now, clicked OK, and it appears on the left hand side here. We want to do the same again, but this time for the beam I'm going to make that a slightly darker colour, and in this case the MP is going to be 4653 in the first direction, which is at an angle of 0, and in the other direction 151, and again a thickness of 0.7 and a unit weight of 24. So we've defined a couple of structural definitions that we want to apply. Now what we need to do is drag those across to the appropriate positions on our geometry. So I've applied the slab, and now I've applied beam structural definition properties. Here in the centre of this line here is going to be where we're having a column soon, so I'm not going to apply any structural definition to that. Also, there are various ways that you can do this, so if I click on a solid here, we can see on the right hand side we have a property editor, and it's telling us, if I just expand that slightly, that it has one structural definition assigned, and that is the slab. If we wanted to change that, I can click in that and change and select from a list. So there are various entry points into changing the structural definitions for these particular solids. The next thing we want to do, now we have a geometry and we have our material properties, is to actually apply some boundary conditions. So, excuse me, as I mentioned, the first thing we want to do is look at making this point here into a column. So I just delete the solid from there, select the boundaries around the outside of it. In this case it's a column that's going through our floor, so I'm going to select the external boundaries and make the support type of those fixed. So we can see now we've got these X's that are going around the boundary. We also have a column in this corner here. If I select the two boundaries for that, and we're just going to make those simple supports along that edge to represent the sort of simple support from the column in that position. The last couple of things we want to do is along the bottom line we want to make our restraint fixed, and along the right hand side we're just going to make the restraints there simple. So you can see you can very quickly select and assign different boundary conditions. There are also boundary conditions that you can apply that allow you to consider lift off, and also if you have an internal boundary, setting that to be a knife edge load. We're not going to look at that in this particular example, but it is an option that you can use. So we have defined our geometry, we've defined our structural definitions, we have our boundary conditions. The last thing we need to do now is start to look at the loading. Excuse me, and that's all defined and managed through our load case manager. So if we click on the button at the top here, you can see that we have the options for looking at different types of loading, so self-weight loads, pressure loads, line loads and point loads. And we can also see that as it stands, nothing has actually been assigned to the problem. So the first thing we want to do is look at assigning some pressure loads. So if I'm going to add a new one, you see here we've got this called pressure load. I'm just going to call that services, and I'm going to set a value of 0.27 kilonewtons per meter squared for that, and it's a permanent load. We can also add some construction loading, and in this case that's going to be 1.65 kilopascals and a variable load. So we go through and we can define for each of the different types of loading the different ones that we want to be applying for different load cases. So we said that for the props we're going to be looking at line loads and point loads. So in this case we can add a new line load, call it prop 1 and make the load from that 18.5 kilonewtons per meter, and that could be variable. Similarly for the second props, call that prop 2 and make the loading from that a little higher at 45 kilonewtons per meter, but similarly it will be a variable loading. And finally we have point loads. We have quite a few of those that we need to apply in our problem here, but I'll just show you how to do one of them. So we go to add, and you can see a new point loads appeared. We're going to call that column, and it's the dead loading, so that's a load of 800 kilonewtons, and it's going to be a permanent load. Obviously you want to go through and also add things like reaction forces, live loading, etc. for each of the columns, but like I say, we're only going to do the one as it stands. So once we've defined the types of loading and the magnitude of them, what we need to do is then put them into different load cases. So if I click OK here, we go back to the load case manager itself, and we can see that we have load case 1, and we want to select self-weight loading. We want to consider that during the analysis, so we click that. And for the position, if I click change, what I want to do is select everything within that project and apply self-weight loading with it, so click OK. Similarly for pressure loading, if we click select there, you can see that the services and construction loading that we defined earlier are available. So I'm going to select that, click change, and again select everything. And actually, while we're here, one of the things we're looking at is the action type. So what we need to be doing is looking at whether it's neutral, unfavourable or favourable. In this case, self-weight loading and pressure loading that's acting downwards is going to be unfavourable, so obviously we would select that in the drop-down list. Similarly, we need to say what we are applying our adequacy to, so what do we want to increase in the problem in order to try and drive collapse. So maybe we don't want to be increasing the self-weight load, but we do want to know what the factor on the service loading or the construction loading and things like that might be. So for the self-weight loading here, we've set it to false. For the pressure loading for the services, and similarly the construction loading and any line loading and etc., we would set that to true. So if we go to line loading now, we can have a line load from our prop. I'll just set a sort of a representative line load rather than one that we're actually going to use. So if I see here, it's already got some coordinates. If I click change, we can just select on the model itself where we want that line loading to apply, and you can see now it's there. Similarly, we can do it for point loading. So if I just scroll this down, we've got the dead loading from the column. If I click change, where do we want that column to be applying its load onto the system, and if I click a point on the left hand side there, we can see now that that's been entered into it. So we've added a few different types of loading. If I just click OK, and then this green button here will show us the loading that's been applied. We can see the red lines around each of the different zones is representative of the pressure loading. The green line here is the line loading that we've got from some of the props, and the little pink load, if you can see there, is representative of the point loading. So we go through all of this and we specify all our different loading for our particular load cases. If we wanted to look at different types of loading in different load cases, we can do that again through this load case manager. So we would just click the new tab at the top, and we could have a second load case that would be considered during the analysis, and it would identify whichever would be the critical case and show that to the user at the end. But in this case, we're just looking at the one. So the final thing we want to do before we solve is just look at the partial safety factors that we're applying. By default, we have unity partial safety factors applied, but what actually we might want to do is create a new set based on our own wishes, depending on which codes we're looking at and things like that. So what we're going to do here is look at a new case that we're going to call ULS. oh sorry, and we're going to say, okay, permanent loading multiplied by 1.4, variable by 1.6, and accidental by 1.2. If we leave the factor on the material strength to 1, then this is going to be our ULS partial safety factor set. So if I save that, we can see now that that's now going to be applied in load case 1. If I click OK, we have all the elements now that we need to solve our problem. So we've brought in the geometry, we've applied some structural definitions, we have set everything in terms of loading and in terms of partial safety factors and boundary conditions. So the last thing we need to do is actually solve it. So what I'm going to do is actually, I won't solve this one, but what I will do is open the file that I prepared earlier. So if I just click on that button, you can see now we've got a lot more line loading and several more point loads in there. If I click the solve button, then the software is then going to examine a few different failure mechanisms, use the optimization and the DLO as Matthew explained earlier, and what we can see is very quickly is come up with a failure mechanism that involves basically a corner lever on the edge of this slab here and going through the beam. And if we look at the bottom of the screen here, we have an accuracy factor that's 1.214. So because we've already applied partial safety factors to it, we can say that according to that, this problem is safe. So we've got a factor of 1.2 over and above what we wanted, including the partial safety factor. So we're looking for 1 or above. We've got 1.2, so we should be happy with that. Very quickly, we can just also make a report based on that. So if I click report, we get some options as to what we want to include in it, and I click OK, and you can see that we have a summary that tells us what the adequacy factor is, shows us what the critical failure mechanism is, and then explains all the pertinent points about the geometry, etc. in there. So that was the first example. That was quite a complex one. Hopefully the next one will be a little bit quicker. So if I just bring that down. Second case is plant loading, and what we have here is a quadrilateral slab. It's quite thin, supported along 2 edges, and the contractors want to take a plant vehicle, so maybe a sort of a mini digger or something like that, up to the right hand side here. We have an additional superimposed loading of about 4.5 kilonewtons per meter squared on that slab, and what we want to ask the software is, can the slab carry the proposed loading at the ultimate limit state? So if we go back to the software, what we want to do is, if I go back to open, look at this, we can see here we have the geometry of the slab, and we've already defined our structural definition for it. So you can see here that the MP values are a lot lower than the building slab that we were looking at previously. And if we then look at the load case, what we can see is that we have self-weight loading applied, this superimposed loading of 4.5 kilonewtons per meter squared that we spoke about just now, and also the thing that we want to be thinking about is the point load. So what we're doing is representing each wheel of the vehicle, and it weighs 11 kilonewtons for each wheel, as a point load. And if I click OK and show that, we can see here that these 4 point loads are on the left hand side. Actually 2 of them are just off the slab, but 2 of them are just touching, so they're going to be imparting some load on there. And then what we want to be able to do is to move this vehicle across from the left to the right hand side of the slab. So what we want to do here is we want to select superimpose load and the 4 wheel loads, and then in the action drop down here we just say copy, and what we want to do is offset it, in this case by 1 meter in each load case, in the X direction but not in the Y direction. So I'll put 0 for that, and I'm going to make 6 copies of that load case, moving 1 meter across from left to right each time. So I click OK. We have a warning that just says that self-weight and pressure loads don't offset, so we don't want to offset any pressure loading by 1 meter each time, so that's okay. I'll click that, but what we can see now is that we have a series of load cases set up in our load case manager. We have an ultimate limit state partial safety factor set again, which is at the top, as we did previously. If I click OK, what we can see now is that we have different tabs along the bottom of the viewer that show that load moving from left to right, and we can also use this spin box at the top to move it across. And what we want the software to do is to just examine each of these in turn and then tell us which is the critical case. So if I click solve, we're just getting a warning about self-weight of the vehicle, so we're okay there, we don't mind about that. What's happening is, you can see very quickly, it's actually moving those loads across the slab and telling us which is the critical case. So in this particular one, it's load case 6 of the 7 that we are examining that's the critical one, and we can see that it's when, if I turn on the viewing of the loading, it's when the vehicle is completely on the slab but towards the right hand side. And if we wanted to scroll through, we can see the different load cases and the different failure mechanisms that we get. And again, just very quickly, we can see that the minimum adequacy factor is about 3.6, so we would be happy, because we've already applied the partial safety factors to it, that this will be safe in this particular configuration of loading. So that's it for the 2 different examples I was going to show. So I'm just going to come on to the conclusions now. So what we've seen today is that yield line method provides quite a powerful means of analysing the ultimate collapse limit state, but the lack of a general computer-based implementation has limited usage in recent years. However, LimitState SLAB addresses this for you. And for buildings, LimitState SLAB can be used at either the design stage or to show that an existing slab has additional reserves of strength that may not have been identified using elastic analysis methods and things like that. Finally, before we just get onto the questions, I'd like to just let you know that recently the price of slab has been reduced, and until the end of May there is the opportunity to get an extra 20% off this reduced price. So you can see, for example, in a 12-month lease license, that the price is now down to nearly £100 a month, which is very reasonable. And if you are interested in that, then there's a code that you can use, and you can use that online or when you order in person. So the last thing we need to do is just look at some questions quickly. I'm just going to take a quick second to see if any have been asked. If you do want to ask one, then please use the functionality to input that and we'll get around to it. Okay, so I've had a question about liftoff. So it's basically asking what we meant by that. So what we can do is very quickly, because I realise time's running short, is I'll make a rectangular slab, and I'm just going to make it 4 meters by 4 meters, and we can have simple supports on each of the edges. And if I solve this problem, what you'll see is that we get a failure mechanism that is a sort of traditional cross shape, and we have yielding around the edges. If I unlock that and then just select the 4 edges, we can see here in the right hand side in the property editor that it's saying support liftoff is false. If I set that to true, it basically says that we can have liftoff that occurs around the edges, and if I solve it again, we now see that we've got a different failure mechanism where in these corners the slab is able to lift up off the supports. If I just bring the animation back down, you can see here that it is similar but definitely a different failure mechanism. And also, if we look at the adequacy factor, we've gone down from 1.5 to 1.39 roughly. So a reduction in capacity because of that liftoff. And I think that's pretty much all that we have time for today, and we'll have a look and see if we have any more questions that we can answer for you afterwards. So I'd just like to say thank you to Matthew for his presentation earlier, and thanks to everybody for joining us. Obviously, we will send you out a link to a recording of this webinar so that you and your colleagues can watch it afterwards if you wish, and we'll also be sending out emails occasionally throughout the year just to let you know about other webinars that we'll be holding and maybe offers on LimitState Slab and our other products. So please keep an eye out for those as well. So again, lastly, just to say thank you to everybody for joining us today, and we do hope that you found the webinar interesting and informative, and we hope to see you again soon. Goodbye.